Alright, we're going to look at few more examples of free fall motion. So what do we mean by free fall motion? That is when the object is only under the influence of gravity. So there's no other forces acting on it except gravity. So we're ignoring air resistance. So free fall motion could be up or down. For instance, if I take a ball and I throw it straight up, once it leaves my hand, the only force acting on it is gravity. So even though it's moving up, the only force acting on it is gravity, so it's still considered free fall motion. And when I drop an object, the only force acting on it is gravity, and again, that is in free fall. And that, of course, is ignoring air resistance. So as long as we're not going at high rates of speeds, and the object's relatively small, then we can ignore the air resistance. Alright, here's an example. A ball is thrown directly upward at 14.7 meters per second. A. How long does it take to reach its maximum height? B. What is the maximum height? C. If it is caught at the same height it is thrown, how long is it in the air? Alright, so I drew a little picture here. I have my ball, and we're going to call the initial position when we throw it up at y equals 0. And we have an initial velocity upward at 14.7 meters per second. So part A, it says, how long does it take to reach the maximum height? Well, as the ball goes upward, we know that it will slow down. So gravity will slow it down. Since we have an acceleration down towards the center of the Earth, that's the acceleration due to gravity, which is 9.8 meters per second squared. Since the velocity is up, the acceleration is down, the ball slows down. And so it loses velocity. So it gets slower and slower and slower until the velocity becomes 0 at the maximum height. Now at the maximum height it still has an acceleration. The velocity is still changing. So then the velocity changes direction and starts coming back down and speeds up on the way back down. So the acceleration is not 0 at the highest point. The velocity is 0 at the highest point. So make sure you distinguish the difference between velocity and acceleration. So we know that at the maximum height the velocity will be 0. So we can use our kinematic equation of velocity as a function of time, set that equal to 0, and find out what the time is when the velocity is 0. The velocity is v equals v naught minus gt. So we set that equal to 0 and solve for t, and we get t equals v naught over g. The v naught was 14.7 meters per second. G is 9.8 meters per second squared. And so that reduces to 1.5 seconds. So that's how long it takes for it to run out of velocity. And at that point, it will be at its maximum height. Now, part B, we want to know what is the maximum height? Well, now we know the time it takes to reach the maximum height. So now we just write our position as a function of time. And our initial position we're calling 0. So y equals v naught t minus 1/2 gt squared. So we get 14.7 meters per second for the v naught times the time, 1.5 seconds, minus the 1/2, the g, and the time squared. And that reduces to 11 meters. Notice that this is the same as the distance it falls in the time it takes to reach the maximum height. Since the ball slows down at the same rate as it speeds up on the way down, so on the way up it's slowing down at the rate of 9.8 meters per second each second, and as it comes back down it speeds up at the same rate of 9.8 meters each second, 9.8 meters per second per second. Since those rates are the same, the time to go up is the same as the time to come back down. So once we knew the time to reach the maximum height, we could just say, well, what distance would it fall in that time? And that would be how high it went. So this makes the equation a little bit simpler. We can just use 1/2 gt squared. So we get 11 meters again. What if we wanted to know how long it was in the air? Well, we could use the position as a function of time equation, set that equal to 0, and factor that so we get a t, and we get a quantity of v naught minus 1/2 gt. So t equals 0, we're at y equals 0, and then we set the other quantity, v naught minus 1/2 gt, equal to 0, and we get 3 seconds for that one. So 3 seconds is just twice the time it took to go up. So that would give us the total time in the air. But once we knew how long it took to go up, we just double that, and that's how long it's in the air. Alright, this example. An arrow is shot up vertically. 3 seconds later, it is at a height of 35 meters. Part A, what is the initial velocity? B, how long to come back to its initial height? Okay, so how do we do this? Well, we're given a position after 3 seconds, so we can just use the kinematic equation of the position as a function of time. We're given the time and we're given the position, and then from there we can find the initial velocity. So our position as a function of time is y equals y naught plus v naught t minus 1/2 gt squared. And we're calling our initial position 0, so we don't have the y naught, that term is 0. And then we put in the 3 seconds for the t, and our y, of course, was given as 35 meters. So we have 35 meters equals v naught times the 3 seconds minus 1/2 g times 3 seconds squared. And then we solve for v naught, and we get 26 meters per second. Alright, now we want to find how long it takes to come back to the original height. Well, again, at the original height, we're calling that y equals 0, so we just use the position as a function of time equation and solve for the time. So we got y of t equals v naught t minus 1/2 gt squared, and set y of t equal to 0. I factor the t out of both terms on the right, and we have t times the quantity v naught minus 1/2 gt. So that gives us two values for t. Well, the first one, t equals 0, that's just when we started, so we want the second one. So I set v naught minus 1/2 gt equal to 0, and then that gives us v naught equals 1/2 gt, or t equals 5.4 seconds. So that's the total time it takes to go up and back down. Alright, so that's the end of the examples for vertical motion in one dimension. So if you haven't seen the other video, check that one out. There's a couple other examples for motion in one dimension in the vertical direction. So the next videos I'll move on to motion in 2 dimensions, and in particular we'll look at what's called projectile motion. So we combine horizontal motion and vertical motion together. Hi, Dr. C here. Thanks for viewing this video, and please help support this channel and subscribe. Also, please leave your comments, questions, or suggestions, and I thank you for your support of this channel. I've also included a link to the next video in this series.